OxyHemoglobin. In this case, the hemoglobin is bound to the dioxygen. We can find some changes when we come from the deoxyhemoglobin into OxyHemoglobin. One important change is iron is found to be present in +3 oxidation state, and also its spin state has been shifted from a high spin to a low spin. This we call it as a crossover. High spin low spin crossover can be found in hemoglobin. OxyHemoglobin is a 6-coordinate low spin iron 3. There is also a controversy regarding the oxidation state of iron. Some say that it is iron 2, whereas some others say that it is iron 3. So let us also conclude whether it is iron 2 or iron 3 low spin. First, when it comes to the geometry is found to be a perfect octahedron. Iron is surrounded by 6 donor atoms. It is a nitrogen-rich environment. The 5 donor atoms being the nitrogens, the 6th donor atom being the oxygen. 4 nitrogens come from the porphyrins. 1 nitrogen comes from the imidazole histidine, whereas the 6th coordination site is being occupied by dioxygen. The most important point is the bonding mode. In OxyHemoglobin, dioxygen bonding mode is end-on terminal. This is called as a proximal histidine, and this is a distal histidine. Here we can see that the ionic size of low spin iron 3 is 75 picometer. Since its ionic size is smaller than the core of the porphyrin, that iron will come into the plane of the porphyrin. So here we have depicted that it is present in the plane of the porphyrin. Here we can see it very clearly. Iron is present in the plane of the porphyrin. As the iron comes into the plane of the porphyrin, the distance between the iron and the nitrogens of the porphyrin reduces. We can compare this with the distance in the deoxyhemoglobin. Here the distance is only 1.98 angstroms. Also the distance between the iron and the nitrogen of the imidazole histidine is also reduced to 2.1 angstrom. The bond angle between the iron and dioxygen is around 131 angstrom, and depending on the organism it can also change to 115 to 155 degree. This is the range. The distance between the iron and dioxygen is about 180 picometer, and again depending on the organism this distance can also shift from 180 to 210 picometer. So when it comes to the stability of the iron dioxygen bonding, dioxygen should not bind to iron very strongly. If it binds very strongly to the iron, then the process of reversibility will be affected. If it binds very weakly, the dioxygen may not be transported to the tissue or the cellular level. It may unbound in between. So it is very delicate. It has to be delicately balancing. And one of the best balancing effects or the stability for the iron dioxygen binding comes from the hydrogen bonding from the distal histidine. The stability of iron dioxygen bonding is dictated by the presence of hydrogen bonding coming from a distal histidine, not from the proximal histidine. So to conclude the geometry, OxyHemoglobin has a perfect octahedral geometry. There are no distortions. Also there are favorable pi interactions, and due to these favorable pi interactions there are no rhombic distortions that are present. When it comes to the magnetic properties, well, OxyHemoglobin is found to be diamagnetic. Now when I say OxyHemoglobin is diamagnetic, previously we have seen that iron is present in +3 oxidation state. It is in a low spin state. If it is in +3 oxidation state, there must be one unpaired electron. If there is one unpaired electron, then the magnetic property should be paramagnetic. Then how to explain the diamagnetism is, iron 3 which is present in a low spin state has one unpaired electron, but the dioxygen is now converted into a superoxo form. So iron 2 is converted to iron 3, whereas dioxygen will be converting into a superoxo form. One electron is being transferred into oxygen. Now it reaches a 17 electron system with only one unpaired electron, and there is a very strong antiferromagnetic coupling between the electrons of the iron and that of the superoxo oxygen. Due to this antiferromagnetic coupling, what we find is there is no magnetic property at all, and hence we call it as a diamagnetism due to strong antiferromagnetic coupling. There are some conventions where the iron is considered as +2. So suppose let us take the convention of iron +2 low spin. If it is iron +2 low spin, then it should be T2G6 Eg0, where there is no unpaired electron. But in such a case, the oxygen species is considered as a simple dioxygen in a triplet state. There should be two unpaired electrons and there should be some paramagnetic moment, but there is no paramagnetism. So oxygen cannot be in a triplet state. Another convention is then oxygen should be in a singlet state. If the oxygen is in a singlet state, conversion from a triplet into singlet state requires a greater energy, which is not explained in this convention. So iron is not considered to be in +2 and O2 in dioxygen form. Instead, iron should be considered as +3, whereas dioxygen is converted into a superoxo form. There is also another convention where iron is considered to be in +4 oxidation state and dioxygen is converted into a peroxo form, which I am not going to discuss here. But is there any evidence for the iron to be present in +3 low spin state? We have two important evidences. One is coming from the IR stretching frequency values, where the oxygen stretching frequency value was found to be around 1050 wave numbers. So it is very closer to the stretching frequency of the superoxo form. This is a very strong evidence. Also, from the X-ray photoelectron spectroscopy data, the oxidation state of the iron, it is found to be around 3.2. So 3.2 is very close to 3. Hence, the iron must be present in +3 oxidation state instead of a +2 oxidation state. And then coming to the absorption of the electronic spectrum, two peaks were found in the visible region, one around 451 nanometer and the another one around 476 nanometer. The transitions are due to pi to pi star intraligand charge transfer transitions, which is also interfered by dioxygen binding. So it is also said that there is ligand to metal charge transfer transition from dioxygen into iron along with the pi to pi star intraligand charge transfer transitions, which is giving color to the OxyHemoglobin. So we say the color of the OxyHemoglobin is purple red or red.